Thanks for the generous introduction, and thanks to the organizers for inviting me. It's a really nice conference. Um, so I wasn't quite sure about the level that the talk should be. So I kind of the first half is for a general audience, the second half is more technical. I kind of organized it that way, but I don't know if that'll work. Uh, so. Um, so what are lattice gauge theories? So first of all, there are these objects called quantum Yang-Mills theories. These are the constituents of the standard model of quantum mechanics that describe interactions between elementary particles. Oops. And lattice gauge theories are discrete Euclidean versions of quantum Yang-Mills theories, in short. And these theories, even without passing to the continuum limit, the discrete theories themselves can yield substantially physically relevant information. So there are large simulations that people run on supercomputers to get information about lattice gauge theories and compute or approximately predict masses of elementary particles. So these are important objects. Um, Okay, so two very important questions about lattice gauge theories, important questions about quantum Yang-Mills theories have lattice gauge theoretic formulations. So let me tell you about that a little bit. The first is a question of Yang-Mills mass gap. And in lattice gauge theories, which I'm going to define soon, mass gap is equivalent to exponential decay of correlations. So you have to prove that certain correlations decay exponentially. And this has not yet been proved mathematically in the most important cases. So these are open questions. And then there is this other big question of quark confinement. So, so this confinement of quarks. So quarks are particles that make up, let's say, neutrons and protons and other particles. And it's mysterious why they're never observed freely in nature. And this problem has received a lot of attention in the physics literature, but there is no rigorous proof. I'll tell you what's the mathematical formulation. And in 1974, Ken Wilson argued that quark confinement is equivalent to showing that, or not equivalent actually, it follows from what's the relevant lattice gauge theory satisfies what's now known as Wilson's area law. Okay, so what am I going to talk about here? There is this longstanding physics heuristic working in the originating in this work of 't Hooft, that quark confinement is a consequence of unbroken center symmetry. Now, I will give a mathematical confirmation of this heuristic. So this unbroken center symmetry is not rigorously defined. So I'll first give this rigorous definition of center symmetry as best as I understood from the physics literature. In lattice gauge theories, and then I'll prove that a theory is confining when center symmetry is unbroken. Okay. Additionally, I will give a sufficient condition for unbroken center symmetry, which is possibly not a necessary condition, but I'll show that if the center of the gauge group is non-trivial and correlations decay exponentially under arbitrary boundary conditions, then center symmetry doesn't break. But possibly, there are better conditions, and but at least it gives you some kind of a foothold here. Okay, so this is about 3 years ago. This paper, it's based on this paper. Okay, so let me define what are lattice gauge theories. Let n and d be two integers, and let G be a close connected subgroup of the unitary group UN, and let Bn be a discrete box, minus n to the d, intersection z to the d. And let En be the set of positively oriented nearest neighbor edges of Bn. So you have nearest neighbor edges, but positively oriented. These are directed edges going from the vertex that's lexicographically smaller to the one that's larger. Okay, so these are directed edges. And let omega n be the set of all functions from En into G. So that is a set of all assignments of group elements to positively oriented edges. This is our space of configurations. Okay, so that's the space of configurations in a pure lattice gauge theory. Then there are more complicated, lattice gauge theories coupled to, bosons and fermions, but I'm not going to talk about those. And if you take a configuration and E is a negatively oriented edge, we define the group element attached to that edge as the inverse of the group element attached to the positively oriented version of E. So that way you have group elements attached to both positively and negatively oriented edges. So that's, you take a configuration and then you extend that configuration with this definition, negatively oriented edges. Is this notation clear? Any questions? Let me know. Okay, so the next thing is plaquette. A plaquette is a set of 4 directed edges that form the boundary of a square. So you have these directed edges, 2 of them are positively oriented, 2 are negatively oriented edges that form the boundary of a square. And let Pn be the set of all plaquettes in this box. And given some plaquette and some configuration, we attach a group element to the plaquette as follows. Yeah. D is the dimension of space-time here. 4, but it can be. For now, it can be anything. Small and fixed. Yeah, and n will also be small and fixed here. So big N is going to infinity, but little n will be small and fixed. So the groups will be fixed. So what are the points of space? Vertices or the edges of this graph? Well, the vertices are the points of space. So what? Okay, so if you want that answer, let me. Yeah, it's a long answer. So yeah, yeah. So okay, so let me see. Okay, so let me give you the answer. So Maxwell's equations are these 4 equations that describe the time evolution of electric and magnetic field paired together. Okay, so at each point of space-time you have 3-component electric field and a 3-component magnetic field, right? So now if you consider space-time as 4-dimensional, you can consider the whole thing, if you consider the magnetic and electric fields over all time, you can consider this as at each point of space-time, you have a 6 vector, 3 electric and 3 magnetic fields, and they must satisfy jointly a certain equation, which will describe the evolution. But if you consider over space-time, you have this equation, okay? So, so Maxwell wrote down these equations. What Hermann Weyl figured out is that these equations, which look strange, this is actually trying to find the critical points of certain action on a certain space. Okay, so what is this action and what is the space? All right. Okay, so so this is the space of all what are called U1 connections on R4. So let me not go into that terminology. So the space of, so you consider all functions, smooth functions on R4 from R4 into R4. So at each point, you have a 4 vector. Okay, so at each point, you have a 4 vector in R4. So you have this, that's called a U1 connection. So I'll tell you more about that. So now this U1 connection, you can write down a certain action on this. Given any such function, you can write down a certain action which is called the U1 Yang-Mills action. I'm going to define the discrete analog of that soon. So you have this U1 Yang-Mills action. You can write it down, and then if you try to find the critical points of that, that'll give you Maxwell's equation. But where does the 6 vector come from? Okay, so you have this 4 vector. And then there is something called the curvature form. So this is a connection form, and there is a curvature form of that, which gives you a 4x4 matrix. So basically, if at each point you have a 4 vector AX, which is A1X, A2X, A3X, A4X, and you write down the ijth entry of the matrix as del AI, del Xj minus del Aj, del Xi, that's the curvature form, okay? So now this curvature form is a skew-symmetric matrix, so it has 6 free elements. So 3 of them are the electric field and 3 of them are the magnetic field, okay? So you have this. So you have this whole setup. Now, what is U1 here? So U1, the Lie algebra of U1 is the real line. Okay. So that's where R comes from. So what Yang and Mills they understood is that if you replace this group U1 by some group SU2, or SU3, these give you the weak force and the strong force. So then then a SU3 connection, for instance, is at each point in R4 you have this four tuple of SU3 Lie algebra elements. Okay, and then you go through the same procedure, and then you have the Yang-Mills action. So this is a discrete version of that. So these group elements that are attached to edges. So from each point, you have D edges coming out. So in R4, you have 4 edges coming out from each point. You have 4 group elements. Now, if you think of the group elements as being quite close to identity, they are like Lie algebra elements. So you have a 4 tuple of Lie algebra elements, and that's okay. So that's the connection. All right. So, but this is a discretization of this whole thing. So let Pn be the set of plaquettes, and for each plaquette, you write it as a sequence of directed edges E1, E2, E3, A4, and you define omega p as a product, omega E1, omega E2, omega E3, omega E4, taking the orientations into account. And now there are these ambiguities in this definition about the choice of U1 and the direction of traversal. So you can fix some convention, but this is not going to matter because we'll only be using these quantities, the real part of the trace of this product, which is invariant under these choices. So it's not going to be important. Okay. So then you define the Hamiltonian of the system as a minus the sum of overall plaquettes of real part of the trace of omega p. Okay. So given any configuration, you compute this omega p for each plaquette. Although the space is d-dimensional, these plaquettes are always 2 by 2 little squares. Okay. So you take, for each plaquette, you take this omega p, take the real part of the trace of that, sum overall plaquettes, put a minus sign as this convention in statistical physics. And then this is your Hamiltonian. So the pure lattice gauge theory on this box Bn with gauge group G and coupling parameter beta and this probability measure, which is proportional to e to the minus beta times this Hamiltonian with respect to the product Haar measure on the space of configurations. Okay, so that's pure lattice gauge theory without any bosons or fermions. It's just like any other statistical physics models that you look at, like ferromagnets, or it's just like that, except that the space of configurations is a bit more complicated. Okay. Any questions about this? Okay. All right. So given a measurable function, the expectation of f under this measure is usually noted by this angle bracket f, as is again customary. Okay, so we'll also talk about boundary conditions. So you have this lattice gauge theory that I defined. I didn't have any boundary condition, it's free boundary. But you can also put boundary conditions. So if you put the positively oriented boundary edges and you look at configurations on these boundary edges, so any such configuration, assignment of group elements to boundary edges will be called a boundary condition. And given any boundary condition, the restriction of this measure to the set of all configurations which agree with this boundary condition is known as lattice gauge theory with this boundary condition delta. So I had free boundary condition, but you can also put, restrict the, constrain the boundary edges to take certain values, and that will give you a boundary condition. Okay, so what's Wilson's area law? Let pi be a finite dimensional unitary representation of the group, and let pi be the character of pi. Then you take a closed loop L in Bn with directed edges E1, E2 up to Ek. And then you define the Wilson loop variable attached to this loop, and fixing this character chi is the character of this product. So you take the product along this loop, taking the orientations into account, and you get this. So that's the Wilson loop variable. And the lattice gauge theory is said to satisfy Wilson's area law for the representation pi if the Wilson loop expectation has this behavior that for any rectangular loop L, but you can also talk about more general loops, but with rectangular loops there is no problem or nothing to discuss about what's the area enclosed by L. It's just the length times the breadth. But if you take a general loop, you have to talk about its minimal surface area enclosed by the loop. So so this Wilson loop expectation is bounded by it's decaying exponentially in the area enclosed by the loop L. And where these constants don't depend on the size of the box. So, in statistical physics, people talk about infinite volume Gibbs measure. We'll talk about infinite volume Gibbs measure soon. But right now, we have a finite box, but you don't want these constants to depend on the size of the box. Okay. So these should be independent of the size of the box. And if this property is satisfied, it's the theory is said to satisfy Wilson's area law. So this is kind of a little strange because you have this long loop going around, and with exponential decay of correlations, you would expect that the product is bounded above by e to the minus the perimeter of the loop, the length of the loop. And in fact, you can prove that. You can prove that quite generally that these theories satisfy a perimeter law. So the expectation is bounded by e to the minus the length of the loop. But why is it the area enclosed by the loop? So that's a mystery. Okay. Yeah. 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 Yes. Yeah. So that's not clear, exactly what it means. So if you can construct in 2 dimensions, you can rigorously construct the scaling limits, and there's a lot of literature. You can do it in 2 dimensions. In 2 dimensions, you can show that quite generally the area law holds, even in the continuum limit. Now, in 4 dimensions, which is a really important case, or even in 3 dimensions, it's not clear in what sense the area law will hold as you take a scaling limit. I mean, because first of all, we don't know how to take a scaling limit rigorously. So, I've had discussions with physicists, and I have this survey called Yang-Mills for probe lists. There's a little survey paper where I try to explain what may be expected to happen as you take a continuum limit in higher dimensions, in 4 dimensions in particular. It's not quite clear even that Wilson loop expectation as defined as this, in the continuum setting, it's the parallel transport along the loop. Even that makes sense in the continuum limit in 4 dimensions. So maybe you have to define it in some other way. You first have to take a smoothing of the field by taking a Yang-Mills heat flow or something like that. So it's not clear what may happen, what may be the analog in 4 dimensions, in higher dimensions. But in 2 dimensions, it's all right. It's not obviously related, and it's not clear how it may be manifest in the continuum, because all that the phases do in the continuum in dimension 4, for instance, is perturbation theory. So that's one of the reasons why this question of constructing the continuum limit is quite important, because this area law is something that's not coming up so much in perturbation theory. So it's hard to understand from perturbation theory. And all that the physics can do at this moment is perturbation theory. So again, it's not completely clear. Okay, so anyways, what is the argument that the area law implies confinement? So roughly, this is how it goes. Let VR be the potential energy of a static quark-antiquark pair separated by distance r. Now, these QFT calculations that Wilson did imply that for a rectangular loop of side lengths r and t, in the continuum limit of SU3 theory with a suitable representation, this should behave, this, this Wilson loop expectation should behave like e to the minus VR times t. So you can read off this VR, the potential energy between quark-antiquark pair, from this Wilson loop expectation. Okay, and here, t has to be bigger than r. I forgot to mention that. So if the area law holds, then VR grows linearly in the distance r between the quark and the antiquark. By the conservation of energy, this implies that the pair will not be able to separate beyond a certain distance, because it starts with a certain amount of energy, and if it goes beyond a certain distance, it will cross that energy, so that's impossible. So that's why it cannot separate. So you can see from this that for confinement, it's not really necessary to have the area law. If you just have VR going to infinity as r goes to infinity, that is sufficient. But it's expected that VR grows linearly in R. So just VR growing to infinity is okay. All right. Well, it depends on the theory. So it should be, it should be true for general representation, unless maybe if the representation is abelian. Yeah, I think it should be true. It's not. So it's like, for each representation you have an observable and the test with various representations. But mostly you just take the fundamental representation. So you just take the product of the group and you work with that. Yes. Yes, yes. So I'm coming to that. Yes. No, the potential energy grows. So the potential energy is VR. So if VR goes to infinity as R goes to infinity, the potential energy will become larger and larger as the particles move apart. You see, so if it was gravitational potential, that would be decaying. For gravitational potential, it's decaying like 1 over R. So that's where you get the forces like 1 over R squared. But here, it's supposed to be increasing. So that's why they cannot separate. Okay, so it is conjectured that the area law holds when a certain symmetry of the lattice gauge theory is known as center symmetry is not broken. So what does that mean? So to my knowledge, there is no rigorous definition of center symmetry prior to what I did in the math physics literature, nor a discussion of what this means for the symmetry to be broken. Okay. And so in this paper, I proposed a rigorous definition, and it's inspired by the physical definition of center symmetry by Polyakov loops, which I don't fully understand, but it's pretty close. Okay, so let me try to define that. So instead of the lattice z to the d, fix a positive integer n and consider the slab 0, 1 up to n cross z to the d minus 1. So one coordinate is restricted to take only finitely many values, 0, 1 up to n. Let ES denote the set of positively oriented edges of this slab, and PS denote the set of plaquettes of this slab. The slab has two boundaries, namely the top boundary where the first coordinate is n and the bottom boundary where the first coordinate is 0. Okay, so there are these two boundaries. And let del E denote the set of all boundary edges of the slab. So now it is an infinite slab, so there are infinitely many boundary edges. Okay, so let's call an element of G to the del E a boundary condition. So a boundary condition of this infinite slab is an assignment of group elements to these boundary edges. So given a boundary condition delta, let omega denote the S delta denote the set of all omega that agree with this delta on the boundary. And define the formal Hamiltonian just as before, but now on this infinite slab. So this is formal because the sum is an infinite sum, which doesn't converge. But you can write it down formally. It's a sum of all plaquettes in the slab of the real part of trace of omega p, where omega agrees with the given boundary condition. Okay, so you have this this boundary condition, and you have this formal Hamiltonian. So, many of you know this, but let me still tell you. An infinite volume gives measure with this Hamiltonian, this H, and a coupling parameter beta is a probability measure on all configurations in infinite slabs, so that the conditional distribution of finitely many coordinates given the rest are exactly what they should be if the whole system formally has this probability density. So that's how infinite volume measures are defined in statistical physics. You know, it's all any probability measure, you know, on this set of all configurations, so that finite dimensional conditional distributions are exactly what they should be. Okay, so these are infinite volume Gibbs measures. So unlike infinite volume, there may be multiple, you know, infinite volume Gibbs measures. Okay, is this idea clear? You know, it's a standard thing in statistical physics, but if you haven't seen this before, it can be a little difficult to grasp. Okay. So note that there may be more than one infinite volume Gibbs measure. There is always at least one. You can prove by some simple compactness argument that there is at least one infinite volume Gibbs measure, but there may be more. So typically, when you say there is the system has a certain symmetry, it means that there is a certain transformation which this such that this formal Hamiltonian is invariant under that transformation. If you take a configuration omega, apply the transformation, formally H should remain unchanged before and after the transformation. That's called a symmetry. And the symmetry is said to be unbroken if there is, you know, well, let me come to the definition. So, yes. Well, the thing is, lattice gauge theory by definition is gauge invariant. Well, I'm putting boundary conditions here. So if you put boundary conditions there, then you have to consider gauge transforms which do not change the boundary condition. So gauge transformation in lattice gauge theory is you take a configuration, on each vertex of the lattice you have a group element, and that induces a gauge transformation by the following. If you take an edge E and you take the group element attached to the edge E with endpoints x and y's, let's say GE, and then you have hx and hy are group elements on these vertices, then the new element attached to that edge would be hx, ge, hx, hy inverse. So that's the gauge transform. And the lattice gauge theory, this Hamiltonian, is invariant under those gauge transforms. So that's one great thing about lattice gauge theories, is that they're by definition they're invariant under gauge transformations. And when you have a boundary condition, you just have to ensure that the gauge transformations doesn't affect the boundary. So you keep the boundary elements as they are. So you have group elements attached to non-boundary vertices only, and that preserves the boundaries. So yeah, this is invariant under gauge transformations. Yeah, yes. Um, yes, yes. So yes, so you can constrain, put that constraint. But right now I'm not. So I'm just taking an infinite volume Gibbs measure. But it'll be sufficient. So I'll only be considering local observables. So it should be sufficient. Okay. So now consider the following transformation on the space of configurations. Take any element G0 in the center of the group. So first of all, if G has trivial center, there is going to be a problem. So assume that G has non-trivial center. So take any element in center of the group, that is an element that commutes with all group elements. And for any configuration, what you do is you take the edge E from the bottom boundary, for each edge E from the bottom boundary going up, okay, replace omega E by G0 times omega E. So you just take all edges which go up from the bottom boundary, just one step, and you replace all of these edges in omegas by G0 times omega. Okay. So call the resulting configuration tau omega. Will refer to tau as a center transform, and this has been used before. Center transforms have been used before in the literature. So since G0 is an element of the center, one can check that the map tau leaves this omega p invariant for any plaquette p. Okay, because for a plaquette you are just multiplying the omegas around, and so if this is multiplied by G0 and this is also multiplied by G0, but then if you're traversing this, this is going in the opposite direction, so this will be G0 inverse, and G0 commutes with everything. It's in the center, so therefore G0 will cancel if you have, and that's the only thing. And if a plaquette doesn't involve any of these edges going up from the bottom boundary, then nothing happens. So this leaves this Hamiltonian invariant. And we'll say that a lattice gauge theory has unbroken center symmetry if every infinite volume given measure is invariant under the action of these center transforms. Okay, so so when you have a symmetry of the system, when you have a statistical mechanics system, a symmetry, as I said, is a transformation which formally replaces, keeps the Hamiltonian invariant, and you say that symmetry is unbroken is if every infinite volume gives measure at a given value of beta, if every infinite volume gives measure is invariant on the action of these symmetries. So that's called an unbroken center symmetry. So as soon as you define what's a center transform, the standard definition of unbroken symmetry tells you this is what it should mean, unbroken center symmetry. Okay. So this is a Gibbs measure. So it's a measure, and you know what it means to say that a measure is invariant under a certain transform. So, okay. No, UN has a center. It's U1. Yeah, but SO3 doesn't have. It has only identity as its center. No, this definition is okay. I'm not saying it has to be. The theorem will say that it has to be to have a non-trivial center. Okay, so we will say that our lattice gauge theory on ZD has unbroken center symmetry for if for some n the theory restricted to this slab under any boundary condition has unbroken center symmetry. So unbroken center symmetry, as I defined, is only on a slab. Now I want to say what is unbroken center symmetry for the lattice for the whole theory, and I define it to be it has unbroken center symmetry for some n, the slab 0, 1 up n up times z to the d minus 1 has unbroken center symmetry as defined above under any boundary condition. Okay. So that's my definition of unbroken center symmetry, and it's very close to what the physicists do with what are called these Polyakov loops, and I will come to that later on, where they take, again, a slab like this, but they don't quite take a slab, they take a periodic boundary condition, and they define it in terms of a periodic boundary condition. Yes? Yeah, so first of all, every definition of unbroken center symmetry I could find, or in the physical literature, what they discuss is in these slabs. So in one direction, they distinguish one time direction and they take a torus in that time direction. And secondly, I can prove that if the theory has, I'll come to this later, if the theory has exponential degree of correlations in a certain strong sense, then I can prove that there exists some large enough n so that this happens. Okay, so this this thing happens in a large enough n. Okay, and the last thing is that that of course defining the center transform, you have to have a notion of the boundary. So that's the boundary seems to be important. Well, Well, it doesn't quite seem to work. If you directly define it on the lattice without first taking a distinguished direction, and it's difficult to work with. So I'm not sure if the theorem that I have here is true. If you define center symmetry without going to a slab, it may be true, but I'm not sure. Yeah, yeah. So here's a theorem that suppose the lattice gauge theory they defined, defined above, has unbroken center symmetry. Let pi be a finite dimensional irreducible representation of G that acts non-trivially on the center of G. So this is where the non-triviality of the center comes in. So the representation that you're choosing for defining a Wilson loop has to act non-trivial in the center. In particular, center has to be non-trivial. Let WL denote the Wilson loop variable for loop L, defined using this representation pi. Then I can show that there is a function V which grows to infinity as R goes to infinity, such that for any rectangular loop, you have this, with R less than or equal to t, you have the Wilson loop expectation is bounded by e to the minus VR times t. So it's an existence result that there will exist a function V, so that this happens. And it doesn't tell you the growth of the function, but it tells you that there will exist a function. Okay. So it implies this quark confinement. Okay. So if you are familiar a little bit with statistical mechanics, you can see that naturally you would expect this invariance of Gibbs measures under the center transforms to hold if you have some kind of decay of correlations. Okay, so this connects decay of correlations with this area law. So whenever you expect these lattice gauge theories to have decay of correlations, you can expect, whenever you can prove, you can expect to get to the area law. Okay. Any questions? Okay, so so let me give you now a sufficient condition, which is not very satisfactory, but it's some condition to have this center symmetry. So recall that omega is a set of configurations in this box Bn, and let us say that a function f on the space of configuration is a local function if it's supported on an edge E, if the function value depends only on the values of the configuration on that edge and on the neighbors of that edge. So you say that two edges are neighbors if they are both edges in a common plaquette, let's say. So given two local functions, let the distance fg denote the Euclidean distance between the midpoints of the supporting edges. And we'll say that a system has strong mass gap if there are positive constants k1 and k2 not depending on n or the boundary condition on Bn, so that this truncated correlation, the expectation of fg minus expectation f times expectation g, is decaying exponentially in the distance between the supports of this local function. So it's an exponential decay of correlations, but in a certain strong sense that it's unaffected by the boundary conditions, and moreover, it's unaffected by how close these are to the boundary. So even if your functions are close to the boundary, you would still have exponential decay of correlations in the distance. So no, the support is, I'm just saying that the support is fixed. So it's just one edge and its neighbors. So for example, it can be shown that this condition holds for any lattice gauge theory if beta is sufficiently small, depending on the theory. So that's one thing, but of course you can expect this to hold in a much bigger regime. In fact, it's believed that SU3 theory, the strong force theory of the strong force, the mass gap conjecture says that you should have mass gap at any beta, and we don't know how to prove that now. Even if that is true, is it true in this somewhat strong sense? That's not clear. Okay, so this is another theorem. Suppose that our lattice gauge theory has strong mass gap, then it is unbroken center symmetry and therefore quarks confined. And then you also have Wilson's area law. You can prove that the area law holds. You can show that VR grows like R. So the step to showing this is to show that there is a thick enough slab where this decay will work. Okay, where this center symmetry will be unbroken. Okay. Okay. So it's not quite saying that mass gap implies area law, but it's saying something close. You know, mass gap in a certain strong sense implies area law. Any questions? Okay, so let me try to prove the result. This is the technical part of the talk. So let S be a slab where our theory is unbroken center symmetry under any boundary condition. Let M be the representation of the dimension pi. Let G0 be an element in center of the group so that pi G0 is not the identity operator. So, since pi G0 commutes with every pi G, Schur's lemma implies that pi G0 is some constant times identity, but it's not the identity, so the constant has to be not equal to 1. C has modulus 1, but is not equal to 1. So that's pi G0. Okay, it must be of that form. Okay, so we'll say that an edge is a vertical edge if it goes up, that is, if its endpoints differ in the first coordinate. A sequence of vertical edges that connects the two boundaries will be called a vertical chain of edges. So going from the bottom boundary to the top boundary. Let E1, E2, En be a vertical chain. A vertical chain variable associated with this chain is the product of one element from each of the matrices, pi omega E1, pi omega E2, pi omega En. So any variable that you take one element from pi E1, one element from pi E2, one element from pi En, and take the product of those, that'll be called a vertical chain variable. So since pi is an m-dimensional representation, there are exactly m to the 2n vertical chain variables associated with the given vertical chain. Now you take the slab, but you restrict the slab. So the first coordinate is already between 0 and n, but then you restrict it further. The other coordinates you say are between minus r and r. And a boundary condition on SR is an assignment of elements of G to the boundary edges of this slab, restricted slab. And then again, you define configurations which agree with this boundary. So our lattice gauge theory defines a probability measure on this in a natural way, so this restricted slab. And for a measurable map, let this denote the expectation of f under this measure. So you take lattice gauge theory, you have a slab. The first coordinate is between 0 and n, the other coordinates are between minus r and r. So you have a big finite slab. And then you put some boundary conditions, so there is already some top and bottom boundary condition, but then you also put boundary conditions on the sides and define the lattice gauge theory. Now here is a lemma. So let psi be the unique vertical chain containing the origin. Then there is a function VR, which tends to infinity as r goes to infinity, so that any vertical chain variable has expectation bounded by e to the minus VR. Okay, if well, of course, under the hypothesis of our theorem that if center symmetry is unbroken, then this holds. Okay, so then you can find a function VR so that any vertical chain variable has this exponential decaying expectation irrespective of boundary condition. Okay. So one way to a different way to write this claim is that if you take a fix R, then take supremum over all vertical chain variables, through the origin. So you take the line connecting the origin to the point n steps above, and you take one element from each pi omega. So you take this product. So there are only finitely many choices of f. And then you take this expectation, maximize over all these variables and all possible boundary conditions on the restricted slab. This number that you get as r goes to infinity, that has to go to 0. Yeah. So it's a trivial translation of this. So you are saying that this thing here, as we take supreme over all delta and f, it has to go to 0 with r. So obviously it's bounded by e to the minus some vr, where vr goes to infinity. Okay. So so here's a proof. Suppose the claim is not true, then the above condition shows that there is a real number epsilon and a sequence rk going to infinity. So the sequence of vertical chain variables fk associated with psi and with this vertical chain, and a boundary condition delta k for each srk, so that this holds. So if this condition doesn't hold, okay, so I want to prove that this condition holds. If this doesn't hold, then you'll be able to find a sequence of vertical chain variables associated with this one vertical chain, and a sequence rk and a sequence of boundary conditions delta k, so that this expectation is not going to 0. Okay. So let delta k e denote the group element assigned by delta k to an edge e on the boundary, and passing to a subsequence, we may assume the following: that for each edge in the boundary of the infinite slab, this tends to a limit delta e as k goes to infinity. So this defines a boundary condition delta. So these are compact Lie groups. So for each edge, you have a sequence of elements changing with k, but then you can of course find a common subsequence so that these are all converging for every edge. And then just you can assume fk is the same variable f, so because there are only finite number of vertical chain variables. Okay, and then you take any r and any k so that rk is bigger than r. So since this is bigger than epsilon and this is a weighted average over boundary conditions on this smaller slab of size r that agree with delta k on the top and bottom, it follows that if you restrict it to this fixed weight slab, this is also bigger than epsilon. And then passing to a subsequence, we may assume that this eta k converges to an eta, so some subsequence of subsequence argument. So anyway, I think it's getting confusing, so I'll skip. So okay, so okay, so this is at the end you can show this. So thus we have shown that for any r, there is some boundary condition on this slab that agrees with delta on the top and the bottom, so that there is a vertical chain variable which is bigger than epsilon. Okay, so this is using all the subsequence of subsequence arguments, you can prove this, that you can find a boundary condition delta for the big slab, for the infinite slab, so that for every r, and you can find a function f, the vertical chain variable, so that for every r, you can put some boundary conditions on this smaller sides of the slab, and delta on the top and bottom. The top and bottom boundary conditions are not changing, so that this is bigger than epsilon. Okay, and then using a compactness argument. Okay, so using a compactness argument, you can show that. Okay, so let me also skip this. Let me go to the end. Okay, so use again this soft tools, Sourav's theorem. Okay, so here is what you end up with. So what I finally end up with is that I show that there exists a Gibbs measure, infinite volume Gibbs measure. There exists a boundary condition on the infinite slab and an infinite volume Gibbs measure, so that for this vertical chain variable f, the expectation of f under this Gibbs measure is value at least epsilon. So in particular, it's non-zero. So you can okay. So from the statement that we assumed for contradiction, that suppose the lemma is not true, we ended up constructing a Gibbs measure which has this property, infinite volume Gibbs measures, which has this property that a certain vertical chain variable has non-zero expectation. Okay, but then we show that that is impossible. So under the center transform, f transforms to c times f. So remember that pi g0 is c times identity for some c not equal to 1. So f, any vertical chain variable will transform to c times f if we apply this transformation. So it means that if the center symmetry assumption holds, then the expectation of f should be equal to c times the expectation of f, which means that the expectation of f has to be 0. Okay. So for any vertical chain variable, the expectation must be 0 if the center symmetry remains unbroken. And with our assumption that of this lemma, we prove that that is not true, which gives you a contradiction. So this proves the lemma. Okay, so this proves the lemma that for any vertex. Okay, let me just recap the lemma. It shows that if you take the slab and take a vertical chain variable, its expectation decays, as the size of the slab goes to infinity. So irrespective of boundary conditions, as long as you have a fixed boundary condition on the top and bottom. Okay, so now the remaining step is to bootstrap from the main lemma to get a bound on the expected values of vertical chain variables in finite slabs of arbitrary thickness. So what you do is now you take any t, okay, and you take this slab, and then you can show that in the bootstrapping this lemma, you can show that the expectation of f in this thicker slab of thickness t is e to the minus vr times t over n, essentially. Okay, so this is a bootstrapping step which tells you that you can multiply vr by some constant times t. And okay, so let me just quickly tell you how this goes. So what you do is you take this big slab and you divide up into smaller thin slabs of size n each, like this. Okay, and this vertical chain variable that you have from the bottom to the top, it breaks up as a product of these variables. Okay, and the lattice gauge theory has this nice feature. So this is what comes in important, is that in a lattice gauge theory, if you have these slabs and you condition on the values on these boundaries, then whatever happens between the, within the slabs become independent. They become independent. So this is the Markovian nature of this system. So this is, so then this vertical chain observable is a product of little observables coming from each slab. So the expectation breaks up, the conditional expectation breaks up as a product of conditional expectation. Each of these is bounded by e to the minus vr. So you take the product, it just becomes e to the minus vr times number of slabs. Okay, so it's a bootstrapping step which lets you go from this thin slab to a bigger slab. Okay, and then finally, so finally what you do, okay, let me explain in words, so let me show you all these points. Okay, so when you have a Wilson loop variable, it's a trace of a product of matrices, right? So you have a product of matrices along a rectangle, and it's a trace of that. So what's a trace? It's basically you take individual group elements from these matrices, take the product of these group elements, individual matrix elements, take the product of these matrix elements, take its expectation, and sum over all products, right? So if you can show that each of these is bounded by e to the minus vr times t, you are done, because the number of terms in the whole product is like e to the minus r plus t. Okay, so that's much smaller. E to the plus, e to the r plus t. So that's much smaller. So if you can do this individually for these group elements, then you are done. And then, so then what you do is, okay. Oh, is there a joke here? Okay, sorry. Okay, so so you have this Wilson loop, and then what you do is you condition on everything except maybe this region. And this is your vertical chain variable here. And as soon as you condition everything outside this region, you are only left with the expectation of this part, and this is bounded by e to the minus vr plus t, vr times t. Okay. Okay. So and this Yeah, so this wraps up the proof of the main theorem. Um, okay, so it's a trace of, so this is the number of elements that you have in the sum, which defines this trace, and each of them is bounded by this, and this part comes from this decomposing this vertical chain variable into these slabs, and within each slab you use the unbroken center symmetry condition to show that it's bounded by e to the minus VR. So when you take up the product over slabs, you get e to the minus VR times t. And so, okay, so I'll not go into, of course, I'm not going to the proof of the other theorem, which gives you, from mass gap to this unbroken center symmetry condition. Okay, thank you.
Do you have any question?
Yes.
So how is this related to the Ising model?
So it's not related to the Ising model except in the setup. These are both Markovian Markov random fields, and these are Hamiltonian. So I didn't quite get the question. So what? Yeah, so it's a different system. So you, instead of, in the Ising model, you have spins on vertices, now you have group elements on edges, and then you have a different kind of setup. But it's the same class of things, generally.
Yes, I have a naive question. So in this work you did, so it's lattice model, so it's for D. So D, you say it's small, but it's
Yeah, no. This is for all D.
And there is no difficulties in the proof that if you have it's
No.
for every D.
Yeah.
Which is in contrast. I mean, I have very little knowledge on the subject, but which is in contrast when you look at in the continuous setting for the dynamic of whether it's 2D or 3D. When you move from 2D to 3D, there is a jump.
Yeah. So here also there are these phase transitions. So for example, if you consider a gauge group to be U1, if you have a U1 theory, it's known that in 4 dimensions the area law doesn't hold if beta is large. But it's conjectured that if you have SU3 theory, then the area law should hold for any beta, even in 4 dimensions. So you shouldn't see a phase transition. But we don't know how to prove that. But I avoided these difficulties because I sort of assume that if you have mass gap, then you have area law. So that's what it is. But of course, you can see transitions in that, and there are all these challenges. But the goal of this work is to make this connection between mass gap and confinement, or more precisely, unbroken center symmetry and confinement.
More questions?
So you have a VR tends to infinity and R goes to infinity. Do you have a quantitative description of the increasing rate?
Yeah, so this is the part that I didn't give the proof of, which is the second theorem. If you assume exponential decay of correlations, then you can prove that VR is actually growing linearly in R. And then you can have the actual area law. Okay. But if you just assume what is unbroken center symmetry, so I define center transform, and that automatically implies the definition of what is meant by unbroken center symmetry, then you just have that VR goes to infinity.
Okay.
Yeah.
So where in the proof did you use that the group is not related?
Oh, no, I didn't use that. No, but what I did use is that it has to have a non-trivial center. And it's believed that groups that don't have a non-trivial center, like SO3, those do not have confinement. So that's believed. But that I don't know how to prove that. That if you don't have it, if the center is trivial, then you do not have confinement at large beta. That's an open question.
The only way that the unbroken center is the expectations of these vertical chain variables
is 0. Yeah.
If there is no question, let us thank our speaker once again.